Okay, we're going to start on living environment, the origins of life today. We're going to cover slides 1 to 24. That's all for today. Just make sure you have everything turned in that's due today. At a quick glance, I think everybody does. Forming Earth and deep time. The universe began about 13.5 billion years ago. At first, it was pretty much made up of just hydrogen and helium, the lightest elements. But as stars were born, grew old, and died, the heavier elements were created in supernova explosions. This happens when there is enough force to fuse subatomic particles together to make heavier atoms. Maybe? Let me close the door, so.
Not too much. Oh.
All the atoms in the universe heavier than hydrogen and helium are forged by stars.
Stars are really interesting. They don't just sit there. They know because they last so much longer than we do. We think they're permanent.
Stars are the ultimate alchemists. They turn light elements into heavier ones. They get the energy that they need to glow that way. A star begins its life made out of hydrogen and helium mostly. About 70% hydrogen, 28% helium in the case of the sun.
In a star's core, the temperature and pressure are so high that hydrogen atoms fuse together to make helium. Hydrogen fusion releases prodigious amounts of energy, the heat and light of a star.
That's the story for 90% of the life of a star, fusing hydrogen to make helium.
Eventually, though, the star runs out of hydrogen and begins to fuse its stocks of helium, making yet heavier elements.
And so the way it works, and it always works this way, is that it contracts and it gets hotter. And if it can find something new to burn, whether it's the kitchen sink or coal or whatever, it'll burn it.
Helium is taken 3 at a time to make carbon.
You can add one more helium to that carbon and make element number 8, oxygen.
That's a tremendous step forward. You get carbon and nitrogen and oxygen made in stars.
Now this is great because on the board we already have the principal elements of life.
Organic chemistry is the chemistry of carbon.
Carbon fuses next, and still heavier elements begin to form.
Sulfur, argon, chlorine.
Potassium, calcium, scandium. The pace of this gets faster and faster.
Back in the middle, silicon is starting to burn at 3.5 billion degrees, stupendous temperature.
It makes titanium, vanadium, chromium,
Manganese, cobalt, nickel, and iron.
Iron is really the end of the road. It's sort of the nuclear turnip out of which you just cannot squeeze anymore.
It's the end of the game. A star that has relied on fusion has come to the point where it has nothing more to spend.
The star is suddenly caught in a disaster. There's radiation going out from the outside, but deep in the inside, there's no more fuel.
Iron can't fuel the stellar furnace, and so, when a star builds up too much iron, it dies.
The core collapses, it bounces,
And it begins to move out, first slowly and then faster and faster.
and that sends a very sharp wave back out through the star.
And now what was falling down is going out, the whole thing blowing up. And you've made a supernova.
A supernova explosion can be as bright as 4 billion stars like the sun.
A stupendous explosion.
Such outrageous energies overcome the iron barrier, cooking atoms into all the rest of the elements on the periodic table.
So starting down here, you can go copper,
Zinc,
gallium,
germanium,
arsenic,
zirconium, niobium, molybdenum, technetium,
strontium,
rhodium,
lutetium,
antimony,
thorium,
tellurium, iodine, xenon, cesium,
francium,
barium, lanthanum,
tellurium,
cerium,
actinium,
actinium,
xenon,
thorium,
protactinium,
protactinium, uranium. Done. That's enough elements.
Okay.
Just wait till the sun goes up.
All right.
We all
Next
get
slide.
bonded.
Forming Earth. Our solar system began forming about 4.6 billion years ago. as gravity pulled together objects out of a spinning cloud of dust, gas, and other material. That material came from a prior generation of stars which had exploded long before. About 99.9% of that material formed the star that we call our sun. The remaining 0.1% formed all of the rest of the planets and objects in the solar system. Earth makes up about 0.0003% of the mass of the entire solar system. So we are just a very, very small piece of the entire universe. Sweeping up all the matter that became Earth generated a huge amount of heat, forming Earth and its moon. The most current theory is that the last great collision was between Proto-Earth and Proto-Theia about 4.5 billion years ago. One result of that collision was the creation of orbiting matter, which became the moon. Another result was enough heat to remelt the surface of the Earth down to the depth of several kilometers. The result of all this was that Earth started out as a molten sphere of material. The densest of that material sank to the center, so we have a solid iron core of the Earth. The least dense came to the surface and became the crust, oceans, and atmospheres. Then about 4 billion years ago, Earth started cooling off. Earth radiated heat into space and cooled. As the surface temperature dropped, atmosphere, oceans, and outer crust formed. These insulated Earth, showing heat loss. Radioactive decay within Earth and heating by the sun also slowed the cooling. Until Earth had cooled off a bit, life would not have been possible. Life must be more recent than 4.5 billion years ago. The first fossil evidence of life is of bacteria from 3.8 billion years ago. There could have been earlier life, but evidence of that has not been found. Elements in Earth. Earth and the solar system formed from a cloud of matter containing all the elements in the periodic table. That is how we know every element on the periodic table exists on Earth. But there are some that we still have not found yet, but we know they exist, we just haven't found them. Nature has created no new atoms since Earth has formed. All the atoms in you and in your world once floated through space, and many of them were once a star. Deep time. The universe began about 13.5 billion years ago. Earth formed about 4.5 billion years ago. The first fossil, 3.8 billion years ago. However, human history is less than 100,000 years. Time is critical for life to have developed from simple chemicals to the complex world we see around us today. The scale of time and space in the universe is almost incomprehensible, meaning it is such a large number that we can't really grasp it. John, are you paying attention to what I'm doing? Okay. The scale is almost incomprehensible. Metaphors help, but you really have to struggle to imagine deep time. It's such a long amount that we can't really fathom how much time we're talking about. Earth is 4.5 billion years old. The chemical processes we'll be describing have proceeded for about 4 billion years. 4 billion, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros in billion. Given an average human lifespan is 72 years. So we are only 72 years. So I can't even imagine if I were to bring in $4 billion and fill it in this room. I mean, we can't even understand how big that amount or how much space that would take. Deep time and lifetimes. Chemical processes we'll be describing have proceeded. Okay, so here you go. This is how you would solve that. The number of lifetimes, so you take the total years divided by the human lifespan. So you would take 4 billion divided by 72, and that is about roughly 56 million lifetimes. That's a lot of years.
That was money I'd be
Yeah, no doubt. No wonder it's so hard to imagine the evolution of life. Our first records of human history are about 10,000 years old, about 140 lifetimes ago. The process of developing life started about 1 million times further back in time than that. The unimaginably distant past. Like I said, it's so far we can't even really in our brains understand how long ago that was. If we think of Earth as having existed for 1 year, bacteria would have emerged in mid-March. All human history would have occurred in the last half of the second of the year. The last half second. So half a second, if we said all of life was a year, bacteria would have been back in March. All human history would have occurred in the last half second of that entire year. So just such a very, very small amount. Deep time is essential to understanding the development of life. Let's watch another video, maybe. There it goes. Nope. Let me click it over here.